Hi there, and welcome to this session on electrostatics. Today we're going to give a broad overview of all the things that you need to know in order to succeed with electrostatics at the end of the year. Let's get going. Now, with the electrostatics, the most important thing is that you remember the basics, right? So sometimes we get so involved in these really complex calculations and ideas that we forget those really easy things, possibly from grade 10, that might pop up and then cause us to lose marks. Okay, so a positively charged object has a deficit of electrons. So in other words, some electrons were lost and now there are more protons than there are electrons on that object. And a negatively charged object is going to have a surplus of electrons. So that object then gained electrons from somewhere, such that there's now more electrons than there are protons. And the reason we're thinking about deficit and surplus of electrons and not saying surplus of protons is because conceptually the protons are stuck in the nucleus. So without actually removing matter, it's difficult to remove or add protons, whereas the electrons orbit the nucleus, and so they are more easily able to come and go when objects gain or lose charge. Right. Then like charges repel and unlike charges attract. And then if two charged objects are touched together, they both become equally charged, where the new charge on each object is Q, as we have it there. So you basically just add up the two charges and remember your positives and negatives for this particular formula and then divide it by 2. It's kind of like the average between two charges. Now, what we've got to do is make sure that we know what we mean when we say 1 millicoulomb. So 1 millicoulomb is 1 times 10 to the negative 3 coulombs. A microcoulomb is 1 times 10 to the negative 6. A nanocoulomb is 1 times 10 to the negative 9. And then a picocoulomb is going to be 1 times 10 to the negative 12. Something else we need to keep in mind is that the charge on an electron is going to be negative 1.6 times 10 to the negative 19 coulombs. And then if we want to convert number of electrons to coulombs of charge, we just use this formula that the charge in coulombs, big Q, is equal to the number of electrons multiplied by the charge on an electron. Okay, right. So now we've got to talk about Coulomb's law. Now, Coulomb's law says that the force of attraction or repulsion between two charged objects is directly proportional to the product of the charges and inversely proportional to the square of the distance between their centers. So we've got this formula here, and in that formula, that force of attraction or repulsion is going to be the F, right? The product of the charges is Q1 times Q2 in coulombs, right? And then that thing about being inversely proportional to the square of the distance between them, well, that's going to be the distance between their centers squared, and remember to use meters for that. So because with charged objects, we often deal with a very let's say a micro kind of frame where things are quite small and not far from each other. We're often given distances in centimeters or even millimeters, and we've got to make sure that we can convert those to meters in order to substitute into our formula. Right, so there we've got the visual representation of what it means if we say the force is directly proportional to the product of the charges. So as the product of the charges increases, so does the force. And then the force is inversely proportional to the square of the distance between the charges. So as the square of that distance increases, the force is going to be decreasing. Now, when we're dealing with Coulomb's law, it's very important that you are able to link what's happening with Coulomb's law with the principle that we get from Newton's third law. Now, Newton's third law tells us that if A exerts a force on B, then B exerts a force on A, equal in magnitude, opposite in direction. And that's going to be true for the electrostatic force of repulsion or attraction that two charges exert on each other. Right? So in this instance here, A and B are going to repel each other because they are both positive. And because of Newton's third law, that force of repulsion is going to be equal in magnitude. So I've written it there as F of B on A and F of A on B, right? So if that's, for example, 10 newtons, then both will experience 10 newtons of force, but A to the left, B to the right. And then the same sort of thing if it's attraction, we're going to have the same magnitude but opposite in direction. And that's why our Coulomb's law equation just has the one F in it, even though there's two objects, because the magnitude of that F is the same for both of those objects. Okay, so now it's time to do some calculations with Coulomb's law. So it says that we need to find the net electrostatic force experienced by Y due to X and Z, right? So this Y here is going to be experiencing a force of attraction towards Z. So I'm going to just draw a little arrow because I know force is a vector, right? So this is going to be the F of Z on Y. And then the X is also going to have a force of attraction on Y, but that's then going to be to the left-hand side. So I'm going to call that F of X on Y. Okay, saying F of X makes it seem like we're doing functions. Okay, so I've got these two forces that are going to be working on Y, exerting themselves on Y, and then in order to find the net force, well, I've got to add them together, but I've got to remember that with vectors, the positive and negative direction is important, so I'm going to have to choose a positive and negative direction as I go along. Okay, so we can use Coulomb's law. So F is equal to the KQ1, Q2 over R squared, right? And I'm going to start with F of Z on Y. And K is a constant, Coulomb's constant. It's 9 times 10 to the negative 9, right? Then the Q1, I'm just going to use Y. So that is going to be negative 3 nanocoulombs. Now, a technique that I use is when I do Coulomb's law calculations and electric field strength calculations, I actually don't substitute in the positives or the negatives. And the reason for that is that if I do substitute in positives or negatives, I then end up getting positives and negatives for the force, which I then have to try and interpret in terms of direction. So instead of doing that, I just put in the magnitudes, right? And then I use the fact that positive charges are going to repel each other and that unlike charges are going to attract each other in order to determine the direction of the force. Okay, so I'm going to go here and say 3 times 10, and then we've got nanocoulombs, right? And we said that's going to be times 10 to the negative 9. And then for Z, I've got 5, and then again nanocoulombs times 10 to the negative 9, and then I've got to go divide, right? So the distance between these two things is given as 5 centimeters, but we recall that we need to put it into meters, right? Now there's 100 centimeters in a meter, so to take this 5 and to turn it into meters, I've got to go divide it by 100, and I'm going to get 0.05. Okay, so this is then divided by 0.05 squared, and then we can use our calculators. So 9 times 10 to the 9 times 3 times 10 to the negative 9 times 5 times 10 to the negative 9, and then divided by 0.05 squared. And then my calculator tells me that we've got here a force of 5.4 times 10 to the negative 5 newtons. Okay, so that's then the magnitude of this force, right? But because I'm interested in Z on Y, right, I know that for Y, the force that Z is exerting on it is a force of attraction. So I'm just going to put here the right because I know that I'm actually finding this vector here. Okay, so that's what I mean when I say I'm not going to substitute in positives or negatives. I'm going to determine the direction of the force by using the diagram, the positives and the negatives. Okay, so then I've got to go and find F of X on Y, right? And that's again going to be equal to KQ1 Q2 over R squared, no surprises. And now we have 9 times 10 to the negative 9. The charge on X is 2 nanocoulombs, so I'm going to go times 2 times 10 to the negative 9. And then Y is still 3, can you believe it? So I'm going to go 3 times 10 to the negative 9. And then here we've now got 3 centimeters, so I'm going to divide by 0.03, and that is going to be squared, right? So now, back to the calculator. 9 times 10 to the negative 9 times 2 times 10 to the negative 9. Oh, I've been using times 10 to the negative 9, and this should actually be times 10 to the positive 9. Okay, so if you ever make that mistake, you're not alone. You're not alone. Okay, so let me just fix that there. Okay, so 9 times 10 to the positive 9. So if you're in doubt, check your formula sheet. So 9 times 10 to the 9 times 2 times 10 to the negative 9 times 3 times 10 to the negative 9 all over the 0.03 0.03 squared. Okay, so see if you get the same answer as me. I got here 6 times 10 to the negative 5 newtons, and I have a feeling that I actually put it in correctly in my calculator. I just wrote it down wrong, but let's double check that answer there. So let's say we've got 9 times 10 to the 9 times the 3 times the 5 times 10 to the negative 9. And then we've got 0.05 squared, and then we can go and say times 10 to the negative 9, and oh yeah, I did put the right thing into my calculator. I just wrote down the wrong thing, so 5.4 times 10 to the negative 5 newtons. Okay, fantastic. Now this 6 times 10 to the negative 5 I know is a force of attraction towards the left. Right, so now all I've got to do is add these two vectors together, right? So I'm going to go F net, and then in order to add vectors together, I need a positive and a negative direction. So I'm going to take rightwards as being positive, I'm going to take leftwards as being negative, and then I've got rightwards for 5.4 times 10 to the negative 5, right? Subtract from that the 6 times 10 to the negative 5, because that's now in the negative direction. And so the net electrostatic force is going to be 1.14 times 10 to the negative 4 newtons. Okay, so, oh, you know what I added? I'm not having a good calculator today, am I? Right, so actually we get a negative answer. Ooh, let's see, so we get negative 6 times 10 to the negative 6. Now remember that we went and we nominated a positive and a negative direction. So if our F net is in the negative direction, that means it's going to the left. So here this negative 6 times 10 to the negative 6 is in the same as 6 times 10 to the negative 6 towards, now I'm right, towards the left. Okay, so this thing is going to be experiencing a net electrostatic force of 6 times 10 to the negative 6 newtons towards the left. Okay, cool.